Hi there. Let's do a few more calculations in a nonprime modulus. And we'll look at a slightly different situation this particular time. So this time we're being asked to calculate 7 to the 29th mod 69. So like before, the first thing we're going to do is calculate phi of 69, which is nice. That works out to just be phi of 3 times 23, both of which are prime numbers, to the first power. So that's pretty straightforward. Since the powers are to the first power, we don't actually, or the primes are to the first power, we don't have to worry about that part. It's just 3 minus 1, which is 2, and 23 minus 1, which is 22. So when I multiply those together, I get 44. Okay? The other thing we want to check is 7 a reduced residue? And it should be fairly evident, I would hope, that yeah, it is, because 7 is a prime number. 3 and 23 are clearly not 7, so the GCD is 1. So it is a reduced residue. However, not helpful yet. So, but I'm going to say yeah, because that'll come into play later on. So we're going to end up having to calculate 7 to the 29th somewhat directly, but not to the point of, like, we're not going to plug 7 to the 29th into a calculator, because again, like what I've mentioned before, even if they have a mod function in there, the number that the calculator stores when it tries to do 7 to the 29th is going to involve some rounding, and that will change the answer. And so we don't want to fully do that. So we're going to use this notion of repeated squaring. Okay? So let me pull, I have a little chart here. Let's pull this up here. Okay, get back. Whoops. Okay, so make it a little bigger. There we go. Well, actually, let's make that a little bit bigger too. Okay, so this is the chart that we're looking at. So there's two pieces to this chart. So we'll talk about both sides of it. So on the left-hand side, so one thing to kind of think about here is that we're going to be using this, again, notion of repeated squaring. And part of the reason we can do this, and this is related to binary numbers, so for those of you that have done some computer programming and you know some binary, this is actually related to it. It's not exactly the same, but it's related. It turns out then when we look at the powers of 2, any number can be built with the powers of 2. So for instance, like pick any number that you can think of. Let's say 733. All we need to do is find all the powers of 2 up to but not greater than 733. So 512 would be the biggest. And we can combine those in different ways to actually create 733. They all add up. It's kind of how binary numbers work. It's why we can represent all of our numbers just using simple zeros and ones in binary, because it has to do with powers of 2. So what that means then is that 29, we can build 29 just by using the powers of the numbers 1, 2, 4, 8, and 16. Okay, so that's kind of the goal here. Okay, so on the left-hand side, the first thing we need to do is we need to actually figure out what 7 to each of those powers of 2 is. So pretty straightforward. Obviously, in the first case, 7 to the first is obviously 7. That makes sense. 7 squared, we can all do in our head. That's 49. Then things get a little more interesting, and here's where a simple calculator can do this. 49 squared is 2,401. May not know that off the top of your head, although you can probably figure it out since it's awfully close to 50. But what is that mod 69? Now, here's where if you have a calculator that has a mod function on it, 2401 is a small enough number with mod 69 that it'll calculate that. We don't have to worry about the issues that I was talking about earlier with the calculator's rounding. There's nothing to round here, okay? So 2401 mod 69 is going to come out to be 55, okay? And then to get to 7 to the 8th, we're just going to square 7 to the 4th. So 55 squared will give us 3,025. And again, using our calculator, we can get that number mod 69 will be 58. Okay. And then, last but not least, 7 to the 8th squared will be 7 to the 16th. So we'll take our 58 and square that, and we get 3,364. And again, mod 69, that'll be 52. Okay, so we know how these various things combine together. So now we're going to build our 7 to the 29th. So I'm just going to start with the highest power, which is generally what we're going to do. So 7 to the 16th. And so I have 7 to the 16th is 52. Well, 7 to the 24th, so I'm going to pick basically the next biggest power of 2 that will fit. In other words, I can add it to 16, but I'm still less than 29. So now I have 7 to the 16th times 7 to the 8th, which is the same as 7 to the 24th. And that's what leads me to this row. Okay, because now I'm going to take 7 to the 16th times 7 to the 8th. And I get 3016 when I multiply them together. Mod 69 gives me 49. And then I'm going to do the same thing again. I'm going to say, okay, now I'm up to 24. What's the next biggest power of 2 that I can add to 24, but I'm still not at 29? And that happens to be 4. So essentially now I'm saying 7 to the 16th times 7 to the 8th times 7 to the 4th equals 7 to the 28th. So I'm taking this number, 49, that I got in the previous step right there, and I'm multiplying it by 7 to the 4th. Okay, so 49 times 55, 2695. In mod 69, I get a really nice number 4. Okay, and then repeat again. I'm not quite at 29 yet, so what's the next biggest power of 2 that I can add to 28 to get to 29? Well, 1 is the only thing, but that's okay. That works perfectly. 2 to the 0 is 1. So last but not least, I have 7 to the 16th times 7 to the 8th times 7 to the 4th times 7 to the 1st equals 7 to the 29th. And so I find out that 7 to the 29th mod 69 is equal to 28. Okay. Now, one thing to kind of point out about this, remember we talked up here, I mentioned that 7 is a reduced residue. It actually doesn't matter. This repeated squaring method works whether it is a reduced residue or not. So we can't use Euler's theorem if it's not a reduced residue, but we can use the repeated squaring method. So that is a tool that we continue to be able to use. And like I said, this is all made possible by the fact that binary number, like we can build all these numbers. We can build all the numbers just by using binary values. So keep that in mind. That's one of the reasons why we are able to do this so nicely. So let's look at one more example. So 7 to the 29th. Remember I mentioned this is not helpful yet. Well, what if instead I ask the question, whoops. What if instead I'm going to look at the problem 7 to the 117th mod 69. Well, now, the reason we couldn't use it up here is because 29 was less than 44. That is not the case with 117. So it just so happens that 117 is equal to 88 plus 29. Imagine how that worked out. So what I can do is I can rewrite 7 to the 117th as 7 to the 88 times 7 to the 29. And here's where Euler's come in now. And this is why the reduced residue piece, it does become important. Because I can rewrite this as 7 to the 44th squared times 7 to the 29th. And because of Euler's theorem, we know that 7 to the 44th is 1. 1 squared is 1, times 7 to the 29th is 28, because we just calculated that. So it turns out that 7 to the 117th is still 28 mod 69. Okay. So what's nice about that is we're mixing together this reduced or this repeated squaring. We're using the fact that 7 is a reduced residue to pull in Euler's method, and we can with fairly low kind of tech methods, maybe a little bit of calculations to find like 49 squared and stuff like that, but we can calculate some really significant exponents within these modular worlds. Like if I put a piece of paper in front of you and said calculate 7 to the 117th, and we hadn't talked about any of this, that's going to take a long time. But if I'm talking about mod 69, like I can do this very quickly. I don't need to multiply out and find out what 7 to the 117th is, because it doesn't matter. I just want to know that remainder. And all of these theorems have been building together to let us get to this point so that we can do this. Okay? See you in the next video.